This problem is from the 2025 Harvard-MIT Math Tournament. Feel free to give it a shot and keep watching to see the solution. Okay, so here's how to do it. We've got three equations and three unknowns. So it's a system of three equations, and we're familiar with solving systems of equations, but this is different. Why is it different? Because of the logarithms in the exponents. So it's going to be hard to work with them later, logarithms in the exponents, so let's try to get rid of them as soon as possible. How do we do that? Well, I'm going to take log base 2 of each equation. Log base 2 of both sides of each equation, but let's focus on the first equation for now. Okay, why did I choose log base 2? You'll see in a second. But right now, the exponent is going to go away. This is going to go over here. So it's going to be log base 2 of yz times log base 2 of x is equal to, I'm going to expand this logarithm. It's going to be a little simpler when we work with smaller numbers inside the argument. So yeah, expand so that you end up working with smaller arguments. Okay. And what does this simplify as? I'm going to just cross these out. Okay. And again, we want to make the arguments as small as possible to keep things simple, so I'm just going to move this outside. So the 4 is going to go here. So it's going to be 4 times log base 2 of 3. Okay, now let's go back to that question. Why did I pick log base 2 of both sides of the equation? Why not log base something else? Well, you'll notice here that, okay, how about this? I'll copy this real quick. We'll do the same thing with the other two equations, and then I'll go back to answering that question. Okay, so if we do the same thing with the second equation, what's the new equation going to be? So that's going to be log base 2 of zx. So basically what I'm doing here is I'm taking advantage of the symmetry. To get from this to this, I just need to go to the next letter. The next letter after x is y, the next letter after y is z, and then once you're at z, you cycle back to x. Okay, so the next letter after y is z, next letter after z, you cycle back to x, and the next letter after x is y. Okay, and then this part of the equation turned into 8, so this part of the equation is going to turn into 9. This part of the equation turned into 4 times log base 2 of 3, so this part of the equation should be what? 6 times log base 2 of 3. Okay, one more equation. Okay, same idea here, go to the next letter. So we cycle back. Same idea for the right-hand side as well. Okay. Let's go back to this question though. Why did we take log base 2 of both sides of each equation? Well, okay, let me make these substitutions first, and then I'll answer that question. Sorry, okay, I know I promised sooner, but it'll make more sense after I do this. first off, why do I need to make substitution? Why am I making substitutions here? This is a new system of equations, but it's still hard to solve because of what? The annoying logarithms. So how do we get rid of them? By substitution. So we're going to change log base 2 of x to a, log base 2 of y to b, and then log base 2 of z to c. Why are we letting a be equal to log base 2 of x? Well, because it occurs more than once. It occurs several times. It occurs 3 times. It's right here, it's also here. Yeah, so wherever there's repetition, you want to think about substitution. Okay, now let's go back to this question. I know I kind of stalled a little bit on that, but the whole reason why we picked 2 here is because that if we didn't, then we wouldn't be able to make these substitutions. The 2 here keeps things symmetric. Keep things symmetric here. Yeah, because like let's say this was maybe 3, then that means this part is going to be 3. This is going to be 3, and this is going to be 3. But we're going to be having 2's here. So then instead of having 3 unknowns here, we'd have, let's see, we'd have 6 unknowns. Log base 2 of x, log base 2 of y, log base 2 of z, and then we'd have log base 3 of x, log base 3 of y, log base 3 of z. Okay, so that's why. Okay, but yeah, the idea here is to make substitutions to get rid of these logarithms, to simplify it. Okay, so what's this going to be in terms of a, b, and c? That's going to be b plus c times, well, this is a. And then, again, if you see repetition, think about making substitutions. I'm going to let this be equal to k because k is just simpler. And I can always change it back later. But what would the next equation turn into? The next equation is going to be, it's the same idea. Go to the next letter because it's symmetric. Same idea here. Okay, so this is much better. This is much better because we don't have those logarithms anymore. And we have constants on the right-hand side of the equations. So this is easier to solve, and well, okay, I'm gonna get another sheet of paper. Let's see here. Okay, so how do we solve this system? I think we should expand, because if we expand, then we can add up all the equations and subtract the first equation from that sum divided by 2. Okay, well that's a lot of steps. That's a lot of steps ahead. But okay, if you don't see all those steps, like immediately, you can notice that there's a lot of repetition if I were to expand out the left-hand sides. AB would repeat, BC would repeat, and then CA would repeat. That's enough of a reason to consider expanding, so let's go ahead and do that. Okay, and yeah, so basically this is a pretty common setup in contest math. with, again, since this is symmetric and this time we're only adding, we can add up all of the equations. And you're going to get 2 times AB plus BC plus CA is equal to this plus this is 22, and this adds up to 20k. So that means AB plus BC plus CA is equal to 11 plus 10k. And then I can just subtract each equation from this to get AB, BC, CA by themselves. Yeah, this is a pretty common setup, so it's just, I think it comes down to pattern recognition. Okay, so if I subtract this from this, what's the new equation going to be? So what's missing here? BC is missing. Okay, so then the right-hand side is going to be what? 11 minus 8 is 3, and then 10 minus 4 is 6. Let's go ahead and do that with the other equations. Okay, so let's see here. CA is missing 2, and then this is 4k. Okay, and then that's going to be AB, and then 6. Okay, no k. Okay, and this is another common setup in contest math. This is simpler than this, so this is good news. I think we're on the right track here. Yeah, but if you see a setup like this, you can multiply all the equations together and take the square roots. So let's go ahead and do that. But before we do that, since we're going to multiply and take the square root, it's probably a good idea to factor out here. Okay, let's go ahead and multiply. So it's going to be a squared b squared c squared is equal to 36 times 1 plus 2k squared. And, okay, so basically we take the square root, so we're going to get ABC is equal to plus or minus 6 times 1 plus 2k. And basically we can divide these equations into this to get A, B, and C by themselves. But, okay. So once we get A, B, C by themselves, what's next? What's the question asking for? Minimum possible value of x, y, z. Okay, so it makes sense why they ask for the minimum, because they're going to be two possible values. Okay. So if we want to minimize x, y, z, well, what's that going to be in terms of A, B, and C? Because that's what we're working with right now, A, B, C's. How can I combine? Okay, so let's look at the substitutions that we made earlier. How can we combine A, B, and C to get something with x, y, z? Something with x, y, z multiplied together. I can add these. So it's going to be a plus b plus c is equal to log base 2 of x times y times z. Okay. So if we want to minimize x, y, z, then that means we would have to minimize a plus b plus c. And so should we take the positive or negative? Should we do positive 6 times 1 plus 2k or negative 6 times 1 plus 2k? We want it to be as small as possible, so we're going to take the negative. Yeah, because if we let it be negative, then all of these are going to be negative. If we let it be positive, then all of these are going to be positive. Okay. So now let's go ahead and divide this and this. Yeah, we can just divide all these equations into here. So that means A is equal to this divided by this, so these go away, and we're left with negative 2. How about B? Negative 3, and then, let's see, C is going to be negative 1 plus 2k. Okay, so that means, okay, so we're going to go back here, because we want to get x, y, z, and we know ABC now. So a plus b plus c is going to be this plus this plus this is negative 6, and then minus 2k. But that's also equal to log base 2 of x, y, z. Okay, so with this equation, how do we get x, y, z by itself? Convert it into an exponential equation. Okay, and how do we deal with negative exponents? Take the reciprocal. Okay, and then what did we let k be equal to again? We made the substitution here. Okay, so k was log base 2 of 3. Okay, so this is going to be 1 over, this is 64, and then times 2 to the power of 2 times log base 2 of 3. I'm going to get another sheet of paper. Oh, sorry about that. Okay. Oops. Here we go. Okay, so 1 over 64 times, I'm going to swap the order here to get rid of the logarithm. Okay, and I can just cross these out, and that's going to be 1 over 64 times 3 squared. Okay, so 1 over 64 times 9, 36. Okay, so 1 over 576. This is your answer.